All right, here we go. All right, so the first ones that we're doing are 1A, so 73. All right, so how do we do that one? Okay, remember how you do the scientific notation? You just move it so that there is a number in between, and then you count how many times you moved it, right? Oops, 10 to the 1, sorry. I'm just gonna make it go up like that, there, like that, right? And then C. All right, the other thing that you have to remember is that sig figs matter when you're doing scientific notation. So that one really only has 3, right? And we're moving it back 3. So times 10 to the third. And why is it positive? It's because it is larger than 1, the number that we started with. So it is always going to be positive if it's larger than 1. E, ooh, this is a long one. 4. And this, every single one of these has to be there. You cannot simplify because it is the sig figs, right, that aren't there. Every single one of those sig figs is in this quantity, therefore we must keep them. And that is 1, 2, 3, 4, 5, 6. No, 5. Hold on, I gotta count. 1, 2, 3, 4, 5. It is 5. Times 10 to the 5th. Okay, so that's how we do those. Okay. So far, anybody need any more explanations of
You
doing?
do be just to be set on the safe
Well,
side.
we're going to do, the next one we're going to do is G, so it'll work the same. And G, okay, so it's a
Okay.
negative, right? Because it is less than 1. And the tip for this one that I gave you the last time, I don't know if you remember, is to count the zeros and then add 1. So it's 1, 2, and 1 more is 3, right? So 5.68. And that was 3. And that's that. And then this next one, I. Okay, so it has 4 sig figs, so we don't need but 2.1, sorry, 2.156, right? And then we need to count how many times we moved it. So 1, 2, 3, 4, 5, 6 times 10 to the 6. Okay, how do we do that? Oops, where's the 1? How do we do that? We moved it so that the number in front each time, if you notice, it's between 1 and 9, right in front of the decimal. Before the decimal, I should say, is between 1 and 9. So 7's between 1 and 9, so is 6, so is 4, so is 5, and so is 2. Now, it couldn't have been 0 and it couldn't have been 10, right? So that's the point on those. And positive if you have larger than 1, negative if you have less than 1. And that's it. That's all that
Okay.
scientific notation is. Yes, ma'am.
So how do we know? So you see, like on how you put 3 numbers behind it.
Yeah.
That's where I be getting confused at. Like I don't know when to put 3 and when to put 2.
Okay. It's a, so it has to do with significant figures. See, if you're just looking at the numbers, this one has 2 significant figures, right? So all of them count.
Oh, before the 0. So we put it.
Right. See, this one
Okay.
only has 3. You see that?
Yeah.
So that's the only ones that would count. This one,
So
all
D would
of
be
them count.
1.78
Yeah, all of them count on that one. Sorry, with D,
because it's no zeros.
1.78. Right, exactly.
Okay.
Times
Okay.
10 to the second. Yeah. See,
Okay.
this one, only these 3 count. Oh, sorry. This one, sorry.
8.43.
Yeah, and in this one, only the 5, 6, 8. In
And
this
then
one, it's only these, right? because
Mhm.
those extra zeros, they don't have a decimal. Now, if there was a decimal here, oops, sorry, a decimal there, then yes, those would definitely be counting, okay? But they don't count because they don't need to in this case.
Okay.
You'll see when we convert it back, like we're doing now. Now we're doing the backwards conversion, right? So we're taking the number and converting it, the scientific notation, and converting it to not scientific notation. So you notice that we have -7. So remember I told you, you add the same number of zeros. So 1, 2, 3, 4, 5, 6, and then the 6, 3. See? Plus 1, -1. In this case, is -1, right? Because it's the opposite. We're going backwards. So let me go up. Ah, wrong one. Okay, for some reason it doesn't want to be big. That's weird. The font is small. Okay, that's too big. Let's make it 10 or 9. There we go. All right, so that's that one. And if you count it, it'll be exactly right. Look, so you go 1, 2, 3, 4, 5, 6, 7. See, it's the same thing. So basically, when you have a negative, just look at the number and add 3 zeros in this case, right? Like this 10 to the -4, you say 0.123, and then add the 5, 6. See? Now, these
Yeah.
are a little more picky. These you actually have to move it. So if we're here, we have to move it 2, making it bigger, right? So 1, 2. So it's 756.8. Boop. Well, it doesn't matter. You can still see it, right? Even if it's small like that. I don't know why it's so small. It is weird. And I'm thinking it's because of that, but look, it's not that. It's weird. I don't know why it's doing that. Anyway, the next one would be G, right? We're doing like pretty much the same ones on each one. So 13. Okay, there we go. All right, so like this, right? This next one is this to the 9th. Okay, so this is a lot of zeros. So we have 3 already, right? So if we move it, it'd be 1, 2, 3, and then we need to add 6 zeros. 201. Oh, sorry, 001, and then 1, 2, 3, 4, 5, 6. There you go. That would be the actual conversion of that one. I just don't like this. This is annoying. Now, see, now it made it bigger. That's weird. Made it really big that time. All right, I don't know what's going on. It's formatted weird. All right, 8.5 times 10 to the -1. Okay. I said add 1 0. But in this case, you don't need to add a 0 because all you're moving it is 1, right? So 0.81. Because all you're moving it is 1 back. Oh, sorry, 85. What did I say? 81. And that's it. That's basically how you do all of these. You just kind of move the decimal. And remember, negative means smaller, right? And positive means larger. So if you're moving it to the right or to the left, that's your business. I like making it smaller or larger. That's the way I like to think of it. And I'll just make these bigger so you can see them better. Oh, okay, no, not you, you. Okay, and then this one. This one you can actually see, okay. I don't know why it's just being so annoying, but there you go. All right, so that's how you do those. Okay, that's the conversion from scientific. Now this one, we need to do each one separately. So I'm just going to go ahead and give you the hint that each time that you're doing one of these, you have to go to your, remember your conversion chart that I gave you?
Yeah, we got it.
Okay, so you notice this one is liters to centimeter cube, and a centimeter cube is equal to 1 milliliter, right? So basically what you're gonna do is you're gonna do 8.79 times 10 to the negative 4. And then you're gonna put times 10 to the whatever the conversion is, times 10 to the what. Okay, so we're going from liters to milliliters, so it's 10 to the third. 10 to the third, and that looks like 103. That's why I always fix it. All right, so that's what we're getting. Now, the answer to that, remember, is you add the exponents, right? You add the exponents, and the exponents, when you add them, add up to -1, right? So it's 8.79 times 10 to the -1. And that's it. You're done. And that would be centimeter cube or milliliters, which is the same. So there. I know it's getting smaller and smaller every time I mess with it. It's like, what? And it's not that, it's this.
It's been so long since we've done this.
I know, that's why the review's necessary, I think.
Yes, absolutely.
Okay, so let me go tab. I'm just tabbing them over because I know I'm needed to anyway. All right, so C, okay, 117, just put the number, right, times 10 to the what? Okay, so milligrams to grams, we're going up, so that's going to be -3, right? You notice there was nothing there already, so we're just putting the -3. All right, now, when we do that, we're multiplying it. But this is not correct scientific notation. Remember how we do that? We decrease it by 2, 1, 2. So we increase this one by 2. So that would be +2 here. So the answer would be 1.17 times 10 to the, remember? Oh, that should have said +2. Sorry. That should -1, right? So you see, that makes it very easy to convert anything without a calculator even. All right, so how do we do that? Okay, so we said remember how that conversion chart that has the blanks in it? Okay, you're going up, so you're counting up from milligrams to centigrams is 1, to decigrams is 2, and to grams is 3, but you're going up. So that's a negative, therefore the negative here, right? And the other part that I remember talking about is that you need to adjust your M part, so the number part, where you're going 1, 2, right? So we moved it back 2, so that means we're decreasing it 2. So we must increase this one by 2, see? Therefore, we are doing that by 2. I didn't mean to underline it, okay. Because that's weird. And it gives us -1, and that's it. And that is grams. I'm just put the grams there, doesn't matter where it is. Okay, so next one. All right. Remember somebody asked me that they couldn't remember how to do the cubing thing. Okay, this is where you learn how to do the cubing thing. All right, so it's 101.3 centimeter cube to meter cube. All right, centimeter cube is what we already have, right? Now, the one thing that you have to remember, and I think I'm gonna insert one of those things just because it makes it easier for me. Yeah, it'll be easier for you too. So let me insert a table with 3. Why won't let me insert a table? Why won't you let me insert a table? Oh, now it will. Okay. All right. So the only reason I'm doing that is so that you see how easy this is. People get confused because it says, oh, it's complicated, but it's really not. All right. So we're changing centimeter cube to meter cube. There is no such a change. So what we have to do is we have to cube each one of the conversion factors. So 1 centimeter, right? And on top is going to be 10 to the, we're going to meters, so 10 to the -2, right? That's on top, meters. How do you look for that? Again, look at your conversion chart and you'll see that you have 2 spaces from centi to to deci, and then deci to meter, right? That's 2 going up, negative. That's why it's 10 to the -2. But we cannot convert this because what they're asking for is cube. And so we need to cube ours. So this is where we're going to do this. And how do we cube? We just put a cube here and a cube here. So when you are cubing an exponent, what you do is you multiplying it. So what is 3 times -2?
-6.
Correct. And that is -6 cubic meters, you see? And then bottom is 1 centimeter cube, see? So now, see, I just did this middle step so that you'd see where it was coming from. Now, all you have to do is multiply it times 10 to the -6, right? So that's our next step here, times 10 to the -6. And again, we don't have the right, and let's take the centimeter cube off because it's not anymore. It's meters cube now, right? All right, so we are now going to do our magic thing that we do. So we go 1, 2, decrease, increase by 2. So this gives us 1.013. Where's my 0? 0.013 times 10 to the -4, right? And that is meters cubed. Does that make sense? What we did just now? Remember, this is
How did you get -4?
because negative.
Okay, I see -6
Yeah, right
plus
there.
2.
And
Negative
where did I get that? It's because I moved it, remember? So we're decreasing it by 1, 2, right? So if we decrease the number by 2, we must increase the exponent by 2. What are you doing with that paper, you little munchkin? Sorry, my kitty. He's grabbing stuff. All right, so that's how you do this one, okay? And that's the only one we have of these, but anything that you have that is cube and you don't have an actual cube for it, right? What you need to do is you need to actually cube it. And that's how it works. You have to cube the number, the conversions that you have. And if you cube, remember, anything that is multiplying, and that's from algebra, if you remember that. Anything that's multiplying an exponent, squaring or cubing an exponent, you multiply that exponent by it. So 3 times 2 is 6, -6, like we said. So that's why the -6 came in. And that's how it works. Okay? Did you get it? Yeah? All right.
Yeah, we get it. We get it.
Yeah, it's actually not a complicated step. It's just something you have to remember, period, you know? Otherwise, it's not going to work. All right, so E, then the next one we're doing is G. Okay, so you tell me. So it's 2.5. We're going from liters to milliliters. What's our direction?
down
Down. How many spots?
1.
No, liters to milliliters. So go to liters. See, do you still have your little chart?
Yes, I'm looking
Okay.
for it.
Okay,
That's so far back.
yeah, I know. That's why I told you, hang on to everything. But yeah,
Yes, yes.
let me
Okay, I found it.
you found it? Okay. All right, so look at it. And liters to milliliters is how many? Remember, you don't count the liters, you just count until you get to the milliliters. So what is that?
I thought I found it. Hold on.
Going. Liters to milliliters.
There it is. There it is. There it is. Okay, so that's 1, 2, 3.
Uh-huh. Going down so that is positive, right? So then all you need is a times 10 to the third. See, this one was an easy one because it was already in the right format. You see,
Yes.
it was already set. And all you need to do is put milliliters now, and there you go. All right, and this last one is milliliters to liters. So what would it be?
That'd be -3.
That's right. See, it's coming back, isn't
Yes.
it? Yeah, it comes back when you do it. That's the main reason why we do this. All right, so next is how many sig figs are in the following numbers? Oh, I think you know these pretty well. If you don't, that's fine. But I think you guys know these. All right, so let's do A.
That'd
How
be
many?
3.
3, right? What about B? And I'm only doing B because it says people. And there's a
4.
about it. Okay, so you would say that's 4 sig figs. And that would be correct. And the reason it's not 1, right, is because every one of those people counts as 1 person. You cannot have half a person. So, that's why it's got to be a whole
What
number.
if it was oranges?
Oranges, you can have half an orange. So, but no, but yeah, that would be probably the same thing. I'm just being silly, but yeah, that would probably be the same thing. It's because it
Okay.
is a unit that is not a unit. You know what I'm saying? It's like 1. Each thing is
Yes.
1. And then this next one, C, is none, right? I mean, it's infinite number of sig figs because what matters, because this is a conversion factor if you look at it, what matters here is what you put in front of it, right? Like we've been doing here. See, like 101.3 centimeter cube to meter cube. Well, that had 4 sig figs. So if that was the conversion, then that would be 4. So, but if it was only 2.0, then that would only be 2. See, so it doesn't matter. It is infinite. So we'll just call it inf. Inf. Infinite. Yeah. So it doesn't matter. Basically, it doesn't have conversion factors. What about E?
4.
4. Yeah, oh, and we said that was 4 too. Okay. Yeah, this one is 4 because even though it has several zeros, all of them count because you have a decimal. And that's what matters. What about F?
10. 1, 2, 3, 4,
Yeah.
5, 6, 7, 8, 9, 10.
Mm-hmm. G?
2.
2. Mm-hmm. Very good. And the reason these zeros don't count is because there is no decimal. What about this next one?
You have to
Is
translate
it
that.
9?
Nope, it is what it says. You don't have to, the 10 times 10 to the negative 12 is just the zeros in front of it. So,
Is it 4?
so 4. Yeah, it's what you see. You know, the number that you see right there, that's how many sig figs it has, period. Nothing, that could have been positive 12, it wouldn't matter. Because remember
So you don't convert that one.
no, you don't have to, because when you convert it, I don't know if you noticed, each time the sig figs matter. So if it's done correctly, then 4 is it. What about I?
3, no. Ooh.
3, no. Ooh.
Do you convert
I
this
cannot
one?
write that. I'm just kidding. What is it? You
Well,
just
if
did.
you don't convert, yeah, if you don't convert the last one, then you don't convert this one. So that would be 3.
Nope, not 3. Why not 3? Do you see a decimal?
Yes.
No decimal, right? No.
Oh wait, where are we at? Oh, this is
We're doing I.
I.
Yeah,
I'm sorry. Okay, so then 1.
1. That's right. It's just 1. And this last one, that was
1, 2, 3, 4, 5, 6,
Mm.
7.
nope, 2. Okay. I don't know if you remember, but
Oh,
basically,
because it's under 1.
if you have a decimal, you start this way, right? Right? So if you have a decimal, you start with that. And the first non-zero digit, like for this one, was 4, because the first non-zero digit you encountered was that one. And then all the other ones counted. If you don't have a decimal, you start this way. And the first non-zero digit you encounter here is 5, right? So that therefore
Yeah.
there's only 2. But if there had been a 0 in between that, then there would be 3. 805, that would be 3.
I
And
see.
see, this one's the same thing. First non-zero digit you encounter is this 4. Therefore, that's the only one. And then this one is the opposite. So the first non-zero is that 2, so there it only has 2. Okay? That's how I do
Okay.
it. To me, this is the easiest way. I don't like this trailing zeros, whatever zeros, and just whatever zeros. I don't like any of that. I just do it the way that I learned it afterwards, and I was like, I wish I'd have known this when I used to do this for my classes, but I didn't. Anyway, so this is how you do it. It's the easiest thing. All right, now converting to the temperature. Okay, so this one requires those formulas. And this one, since you're going to Celsius, requires the C formula, which is temperature is equal to Fahrenheit, right? Minus 32. Remember that one? Divided by 1.8. And this is first, obviously, and then divided by 1.8. 1.8. Okay, there we go. So that's what we need to use for A. Fahrenheit minus 32. So 115. Where are you, calculator? There you are. Okay. 115. Who's got it? Sure.
46.11.
Yep. 46, 4 point, yeah, 46, sorry. 46.11. 46.11. Your number is always going to be smaller if you're going from Fahrenheit to Celsius, right? And according to sig figs, that's good enough. So that's what we're gonna leave. And we know it's Celsius, so we'll just put a big C on it. Okay. All right, what about the next one? It's a negative. So what do we do?
They're not Celsius. Let's see, that would be negative 14 minus 32. divided by 1.8. And then that will equal negative 25.55.
Or 6, right? Negative 25.6 or
Yes.
negative 25.6, and that would be Celsius. Yep. So it makes a difference, right? Where you're coming from if it's negative. So if it's negative, you've got, and like I told you, it's always smaller. And this is smaller, believe me. This is always smaller than Fahrenheit. Fahrenheit's always the larger one. So if you end up with something larger, revise because you did something wrong. Okay, now let's do the opposite. Do you remember this formula?
No.
Okay, so the Fahrenheit formula is, these are some of the ones that they're probably going to want you to know in your test if you're taking one of those. It is 1.8 times C. So times the Celsius, right? And then this first, and then add 32. So now you can do it, right? All right, so 1.8, so 19 times 1.8 plus 32. I get 66.2. That's what I got too. All right, so as you can see, they're pretty straightforward formulas that you can just plug in. So 66.2. And that's Fahrenheit. See how now it's the Celsius, that's lower still. So that had to be a higher number. And that's correct.
True.
All right, so do the next one, D.
Negative 27.4.
Again,
Degrees
we are
Fahrenheit.
still, yep, we are still correct because this is higher than that one, right? Because the lower you are, yeah. All right, now Kelvin to Celsius. Remember that one? You just add 273 to the Celsius. So basically, Kelvin is Celsius plus, I can just do that one, typing it. That'll be easy. So Kelvin is equal to Celsius plus 273, right? So that one's, oh, sorry, minus. Yeah. We're going, this one's 2 Celsius. Yeah, I went backwards. So all you have to do is simplify, solve for Celsius on this one, which Celsius in this case would be equal to Kelvin, sorry, capital C, equals to Kelvin minus 273, right? So that's a capital K. All right, so there's the 2.
Thank you.
So that would give us
325.
325.
Degrees Celsius.
Yeah, Celsius. All right, and now you notice the next one's Fahrenheit to Kelvin. And you have all the tools.
Do you have to? Yeah, you have to convert Fahrenheit to Celsius, then to Kelvin, correct?
Correct, because otherwise you can't.
Right.
But it's easy because, you can just do this formula, right? And add 273 at the end. This formula, and I'm pointing to it, but I know I don't have my thing on me. This formula, right? I'm sorry, this formula, and then add 273 at the end. So basically, it's 23 minus 32 divided by 1.8 plus 273. I get to 68. Is that what you got?
Yes.
Okay.
And that's degrees, well, Kelvin.
Yeah, that's Kelvin. Yeah, which is not a degree thing. But we haven't been putting degrees to anybody because it's harder. But it's still
Right.
good. Yeah, it's just harder to do it. It's more complicated. But all right, now these problems are interesting.
Problem.
Yes. So we're gonna put in a dimensional analysis thing. No, we're not. You'll see why not. Okay, so density is equal to mass over volume. We know that, right? So let me clear these out. So density equals to mass over volume. If we do our triangle, we'll have everything we need. Right? So density over here, mass over here. Oh, that's an M. And that's volume right there. That's an ugly M. Anyway, so notice it says the density of gold. So let's just call it DAU, right? DAU, because DAU is gold. That way it'll be easier. So we're going to say DAU equals 2. And this is just numbers that we need first. Grams per centimeter cube. And I'm just going to put it like that. Okay. So DAU. And then the next thing we have is density of water. So DH2O. H2O. There we go. That's equal to 1, right? 1.00 grams per centimeter cube or milliliter, whatever. In this case, centimeter cube, because it matches. All right. And then it's telling us we have a block of gold that is 5 by 4 by 15. Okay. So that's our volume, right? The volume of gold. So VAU is equal to 5 centimeters, right? Times 4 centimeters times 15 centimeters, which is what? 300, I think. Yes? Because it's 20 times 15 is 300.
Yes, 300.
Okay. And that is the, okay, now look what it's asking us. What volume of water would need to be the same as the mass of gold bar? Okay, so what they're asking us is for mass of AU, right? Don't look at the water yet. We haven't solved that part yet. So mass of AU equals 2. Oops, sorry, equals 2. All right, based on this is density times volume. Okay, so density is 19.3. And we're just going to skip the stuff just because they cancel and you get mass, which is grams. Okay, so what is 19.3 times 300? And we have to watch the sig figs.
5,700.
5,700. 5,700.
Would be 5,800.
Oh, Lord, I could not understand that word you said. No, I have 9.
Oh, what?
Yeah.
19.3 times 300.
No.
Yes,
One less.
790.
Yeah, sorry. One less. There you go. And that is grams, right? All right. So we know that that mass of gold is going to be, now we need to figure out, so we're going to equate this to the mass of water, right? Why? Because it's telling us that that's what it is. All right. So what do we need? We need the volume of water. Not there. I want to put it over here. Hold on, tap, 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 tap. There we go. Volume of water is going to be equal to what? Okay, so we have the density of water and the mass, right? So the mass is what we just figured out, which is 5790, right? Grams divided by 1, right? Because that is what mass over density. Oops, that's times. That's meant to be that. Okay. That's going to be equal to 5,790 centimeter cube of water. Oops, sorry, cube. There. That's it. That's how you solve it. So
Oh,
basically,
good grade.
all you had to do was figure out what the mass of gold was, because the other one's 1, you know. So 1 to 1, the mass of
Right.
water is going to be the answer. That whatever the answer here is, right, it's the same for mass as it is for volume in this case. Now, if it had been silver, that'd have been a totally different story. You would have had to multiply by the density of silver, and then you would have figured that out. But like this, it doesn't matter. All right, now look at this next one. It says calculate the volume of a sheet of plywood with these dimensions. What's wrong with these dimensions? We can't multiply them, can we? Because they're apples, oranges,
Centimeters,
cherries.
meters, millimeters.
Exactly. So we can't. So we need to make them all. What is volume given in normally?
Right. No.
Hmm? That's weird. What is volume given in? All the time. Centimeter cube, right?
Oh, centimeter cube.
So we
Okay.
need to change them all to centimeters, right? Because when we multiply 1 times 2 times 3, it's going to give us centimeter cube. So we need to change very first one. And to do that, remember, and this time, what's going to be good about this one is you don't have to worry about changing it to the normal thing, because you're just multiplying everybody. So it's 2.78. That one's okay, right? That was already centimeters times. The next one is 11.3 times 10 to the what? We're changing it to centimeters, from meters to centimeters to second, right? Centimeters. And then times, the next one is millimeters. So 7.53 times 10 to the -1, right? Centimeters, see? So just multiply all of those, and don't worry about doing anything with the exponents yet. So just do 2.78 times 11.3 times 7.53. You notice that that's the unifier right there. Okay, so I get, and we need to stick to 3 sig figs, so 8.79, right? That's what I get.
Oh, that is not what I got. Hold on. Let me try
Times
that
10
again.
to the, okay. 8.79 times 10 to the 1 is what I get. And then I get times 10 to the 2, right? And then times 10 to the 3. 10 to the -1, sorry. All right, so that is all going to be multiplied. See, that's what I said. Don't worry about it. Just do your math.
How
And
did you get 8.79 though?
because it's 10 to the 1. That, I know it looks like 101.
No, I mean I got 236.54.
Really? Okay.
I did it
Maybe I
twice.
screwed up. Hold on. But the main thing is that, okay, let me do it again. Okay, so clear. Okay, so it's 2.78, right? We're not multiplying by anything right now except for the numbers.
Right.
0.3 times The other one was 7.53. You're right. I got 236. Okay, so it's 236.02, 2.3602. Okay, so this should be 2.365, so 37. Oh, times 10 to the second. Okay, like that. All right, so look, multiply them all. What you get? 2 times 2 times 2. Right, so that's 2 plus 2 plus -1. So 4 -1 is to the third,
Negative
right?
3.4 and 4.
So the answer is 2.37 times 10 to the negative third, positive third, sorry, centimeters cubed. Cube. There you go. And there. That's what I got. Or if you want to give the number in not in scientific notation, what is it?
2.36.5.
No, not in scientific notation. So it would be 2,370. Yeah.
Yes.
See? You just did it. Like I said, don't worry about changing anything because the answer is not final until you finalize it. And then it has to be in correct scientific notation. But by then you already have it in, So if you put your answer as 278, that's fine. Okay, so since I was doing it a certain way, I ended up getting it with times 10 to, the second. But what if it had been 237? All right, that would have still been the same answer, right? Except
Yes.
in this case, you wouldn't have had the 10 to the 2. So that would have been times 10 to the third anyway. You see that? Why? It would have been times 10 to the -1, yes? Yeah, because it's just 2 and 1. No, 2 and 1. No, it is 2 and 1. So 2 and 1, that's, +1, not -1. Okay, and then you decrease it by 2, you increase it by 2, you get 10 to the third, see? So either way, it doesn't matter how you would have approached it, you would have still gotten the 10 to the third, or 2,370, whatever. Does that make sense?
Yes.
Okay. All right. How many seconds in a leap year? First of all, how many days are there in a leap year? I always forget that one. How many?
364.
Or is it 66?
Oh, I don't know. Yes,
I think it's 366. Because think
366.
about it, we're adding a day to
Yes,
February,
yes,
right?
yes, that's true.
Okay, so 366 days. Okay, so one day has how many hours? 24, right? 1 hour has how many minutes? 60. 1 minute has how many seconds? And there you go. 60. And remember this? What do we do? You multiply.
You multiply everything.
Everything, right? Because the bottom is all ones. So you don't need to divide it. So just multiply and tell me what you got.
31622,400.
Okay, I'm just going to put it right here. 316. What?
22400.
Okay. Obviously, we can't have this many sig figs. So let's cut them down to 3. So we go in 1, 2, 3, 4, 5, 6, 7. So that would be 3.16 times 10 to the 7th. Yeah.
3.16 times 10 to the 7th.
Right. Does that also make it more sense. Seconds, right? And I'm putting the answer there, otherwise it'll go on the bottom, and I don't want it to go all the way to the bottom. I don't know why, but oh, that's because I have an extra. I didn't realize I had an extra. Oh, no, I don't want you. I need you going. Yeah, you, the whole thing. Go. The lead entire row. Okay, there we go. That's why I couldn't do it in the bottom. All right, so there's your answer. That was pretty easy, right?
Yes.
Okay, so the next one's not gonna be so easy because it's a very weird question, but it's really neat at the same time. You notice it says a clock gains this many seconds in 1 hour. How many minutes does the clock gain in 365 days? So, okay, 365 days is where we want to go. And we need to change it to hours because the clock gains that much per hour, right? So we need to multiply that. So, oops, let's just put in one of those things again. It won't let me put it in there, so I'm just going to stick it in here. Insert table, let's say 4 again. Okay, and let's start with this number, right? Which goes inside. All right, so we know that 1 day has 60 minutes, no, 24 hours, sorry. We just changed it. You see that? So 24 hours. Now, for every hour, the clock gains 0.050 seconds, right? Isn't that what they told us?
Yes.
But they want it in minutes. So now we need to change those seconds. No, 60, sorry. Yeah, 60 seconds, right? Equal 1 minute. And there you go.
I'm having such a hard time deciding which goes on bottom one, which goes on top.
Okay. The main thing is to be able to cancel out. So if you are doing this,
Okay. I
okay,
see.
so something
remember
has to cancel. See, days have to cancel. And then they gave us this, right? So we know we need to multiply it because otherwise we can't figure out how much it gains. Therefore, hours need to be on the bottom, right?
Yes.
And seconds need to be on the top. And see, that worked because the hours changed. So now seconds need to be on the bottom and we need minutes because that's what the question is.
Okay.
And it should be 7 point something if I'm not mistaken. I've done this one before many times.
7.3.
Yep. 7.3 minutes per what? Year.
Year.
Right? That's right. 7.3 minutes per year. So the answer is 7.3 minutes per year. There you go. Pretty easy when you're thinking about it. Okay, look at this one. This one is what I call a study in uselessness because milligrams per milliliter is same thing as grams per liter because milligrams is 10 to the third, right? 10 to the negative 3 grams, and milliliters is 10 to the negative 3 liters. So basically it's the same number. Yes? Yes or no? Yes. Okay, so if we were to do it, it would look like this. It would look like 23.7 grams times 10 to the negative 3, right?
Right.
I'm sorry, milligrams. That's to change it to grams, right? And that would be equal to whatever. So it would be 23.7 times 10 to the negative 3. And that's on the top, right? The bottom would look like this, divided by. All right, 23.7 again, right? And that would be milliliters. Well, 23.7 is already there. So milliliters would be on the top. And then divided by, that would be what? Or actually multiplied by 10 to the negative 3 again. And that would be liters. So if you look, if you're dividing something, remember how the reciprocal works? The negative 3 comes up as positive 3. And doesn't that give you 0? So basically the answer equates the same. The answer would be equal to 23.7 grams per liter. See, like I said, a study in uselessness because you just got the same answer. Why? Because the parameters are the same for both. Now, if it had been milligrams per deciliter, that'd be different, you know, but it's grams per liter. So it's the same number moving up. And they're dividing each other. Right, exactly. All right, so let's do this one. Insert a table. Let's do it a Ford table like we've been doing. All right, so remember this one is one of those where you have to, oops, that's one too many ones. You have to change both. So what that means is that it travels 115 kilometers in 1 hour, right? So as long as we end up with meters on top and seconds on the bottom, just like we're supposed to, we're good. So 1 kilometer is equal to 10 to the third meters, right? And then that one's it, right? That's what we wanted. So this conversion is over. Meters is what we want on top. Now we need to convert the hours. So we need to say on this one, it's easy. 1 hour is equal to 60 minutes. And 1 minute equals to 60 seconds. And look, this one would have also canceled. As you can see, kilometers cancel, and you get meters on top. This one cancels hours. Minutes cancel minutes, and you get seconds on the bottom, which is what you want because it's meters per second, right? So meters on top, seconds on the bottom. So just multiply, divide, and limit your answer to 3 sig figs, and you got your answer.
That's divided by 60 times 60?
Yep. Yes. And you can use parentheses for that. And by the way, this is not 103. You know that. I mean, it's hard to. This is 10 to the third or 1,000, whatever you want to call it. I always put 10 to the third because it's just easier for me to, you know, think about it because of the direction, right? I get 31.9. Is that what you got? Or
Yes.
Did I mess it up again?
Well, not
No?
exactly. Not exactly. How did you put that into your computer or your calculator?
Okay, okay, I'll show you. I'll type it in like I put it in. Okay, so I put it in like this. And you can put 10 to the third, or you can put 1,000. So I'll put 1,000. That way it makes it easy for you. Divided by 60 times 60. And then equal. That's how I put it in. And if you don't have a 10 to a third, you know that 10 to a third is 1,000. So you can just convert it directly and put the zeros if your calculator doesn't do that.
I got a syntax error. My calculator is not as good as yours.
Yeah, I get to 31.9 meters per second. That's what I get. I should give you that. I don't know why it always gives me a third thing when I don't want one. Delete. Entire row. Yes, go away. There we go. All right. So that's a change, that is what we do when we're doing any kind of what they call dimensional analysis. They're good for any kind of conversion. Now these you're gonna like. Okay, so they're all squaring, every one of these. So we're gonna insert our little table of 3 so that we have an intermediate. Let me get rid of all this crazy stuff. Okay, all right, so what do we want? We want to change 1 meter squared, right? So again, we have to do 1 meter, and we're changing it to millimeters. So 1 meter is equal to 10 to the 3rd millimeters, right? And this has to be cubed. No, not cubed, squared, sorry. Squared, right? So we're going to put the 2, and yeah, I'm going to come back and I'll do all of this correctly, but right now I can't. So I'm just going to, all right, there you go. All right, and then this is also squared. Why do we square? Remember, there is no conversion to the direct square like this. So what you have to do is you have to square your conversion factors, like what we're doing right now. And if you square your conversion factors, you have to remember that rule about the multiplication, right? So 10 to the 3rd times 2 is 10 to the 6th. And that is millimeters squared. See, now we have the right conversion factor. So each one, right? See? All right, so that's the answer right there. The answer is 10 to the 6 for that first one. All right, 1 times 10 to the 6, obviously, but I mean, I always call it 10 to the 6 because there's no need to put that 1 since that 1 was already here and you're multiplying it. So 1 times 10 to the 6. All right, the next one, kilometers. All right, again, we do the same thing. Let's insert our little table in there of 3. Reason I do 3 is so that the middle one is the conversion that we're having to actually perform. So 1 square kilometer. All right, so 1 kilometer down here, right? We're going to have to square it. It's going to be squared. I hear the birdie.
Yes, I'm sorry.
No, he's so cute. I love animals, so, oh, sorry. All right, so we're going to meters, and meters is 10 to the 3rd, right? But we're going from kilometers to meters, so yes, it's positive, right? Yes. And then that is times squared, right? So, oops, sorry, that should be meters under here. All right, so when we take it out of this, we have a conversion of 10 to the 6 again, because we're going, oh, wait, that should have been negative. Oops, I don't know what I did. Yep, that should have been negative. Sorry. Because we're going from meters to, no, meters to millimeters. No, that's positive. This one's the negative one. Ah, this is confusing the way it's written. See, I put 1 kilometer, but it's actually 1 meter. So this is backwards. This one needs to be 10 to the negative 3. Yep. This is the one that's negative. You see why? Because we're going from meters to kilometers, right? And kilometers is up. So this is a negative. So this is actually 10 to the negative 6 square kilometers. See? Yeah. Why? Remember your little conversion thing? You have to go up. Up is negative. Therefore, this is negative. That's why. That's the only reason. Okay. All right. And then this centimeter. All right. So you guys want to do the next one? Oh, come on. Don't laugh. It's not that hard. Centimeter to millimeter. All right. So insert your little 3, right? Okay. So we're going, see, it says we're going to millimeters. So this is what we need to write. We need to write what's on here. So 1 millimeter squared. All right. So 1 millimeter squared on the bottom, right? But we don't have those, right? So we need to square it. And when we square it, what is millimeter to centimeter? How many spaces are we moving and in which direction?
Just 1 up, so it'd be -1.
So 10 to the negative 1. And that would be millimeters, right? Oh, sorry, centimeters. See, I'm getting all confused myself. Square. Okay, so when you square it, remember you multiply it, right? So then that is 10 to the negative 2, right? And that is centimeters squared. So now you have the correct conversion for every 1 millimeter squared. Okay, so what's our answer? Simple. It's right here. Right? There it is. This one, let me make it squared, correct. So it looks better because it looks like 10 minus 2. There, this is our answer. So the answer is 1 times 10 to the negative 2 centimeters. All right, what about the next one? And that's supposed to be decimeters, by the way. There you go. All right, so what do you do with that one?
Convert decimeters to centimeters.
Right, and which is what? What is decimeters to centimeters?
You go down 2, so it's +2.
Okay. So 1 decimeter is equal to +2, so 10 to the second, right? Centimeters. No, 1, just 1.
Just
So,
1?
yeah.
Oh, okay, just 1.
Yeah, it's just 1. 10 to the 1 centimeters. I know that looks like 101. But yeah, you're right about the 2 because we need to square it, right? But we haven't squared it yet. So we need to square it. Once we square it, then yes. And I know it looks like 101, and I know it's a mess right now, but I'll clean it up so it looks pretty. Because otherwise it makes it confusing if you don't see these little things up like they're supposed to be. You know, this is why I always insist on having the right numbers. And this is a 2 also. Okay, well, all right. So when we take it out, it's 10 to the second centimeter squared equals to 1 decimeter squared. All right, so there's your answer. See how if you go up is negative still, right? If you go down is positive, right?
Right.
So it's still the same number, same thing. It's just that you have to square it. If you don't square it, then the equality is incorrect. There's the problem.
So the answer to D, let's say, is 10 to the second.
Yes, 1 times 10 to the second. So right here would be 1 times 10 to the second. That would be your answer. So basically the answer is the last column of each one, right? So this one is the answer to that one. This one is the answer to that one. This one is the answer to that one. And just put 1 in front of it because you are multiplying it times 1, right? Right here. That 1. And
Yes.
yeah. Okay. And that's it. That's how you get them all. It's actually not a hard thing to do. It's just one of those things that you have to, get used to doing, is squaring your numbers if you need to, because there are no conversion factors for square or cube. So you need to cube it yourself and then you convert it. All right.
Okay.
So this one right here, this number 12. Let's see, we still got time. Ooh, we're beyond time if you guys need to go. Do you have a class?
I don't. I can stay. But
Anybody
others have
else?
classes.
Anybody else have a class? No? Because I can keep going. I have no problem. I don't have a class until 12:30.
Okay.
All right. I'll keep
like
going. All right. Nobody said nope. So, all right. I'm going to insert another table. This time, I always try to insert like more than I need sometimes, but that's okay. All right. So look at this. This is the kind of question that you're going to get in your nursing career. All right, so it says Vioxx is a drug used to treat arthritis. If a patient takes 125 microgram tablet per day, how many milligrams of Vioxx are in their 1 month supply? All right,
Oh my
so
goodness
we
gracious.
start with what they're asking us, right? We start with 1 month or 30 days in this case. Okay. Why do we put 30 days there? Because we have our next conversion. Look at that. They're internal conversions in the question. You see that?
Yes.
Okay, so 125 micrograms, right, goes on the top. Oops. Where's my 125? And I'm just calling it MCG because it's what you will see. All right, in 1 day, right? So we're just gonna shorten it to D. All right, now look what it next. The question is not how many micrograms, it's how many milligrams. You see that?
Yes.
So there's the question. So now we need to change micrograms, right, to milligrams. And you know that one because you have your conversion factors right there. So it's 10 to the what?
-1.
No.
Milli.
No,
Milligram.
remember, their blanks are there for a reason.
Wait, milligram. Oh, wait. Microgram to milligram. Microgram to milligram?
Yes, micrograms to milligrams.
That's up 1.
Nope. No,
-3.
count the blanks. It's 3. There are 3 blanks, right?
Value. I see value in units is -3.
Yeah, okay. So that's another thing. If you don't want to count, you have the 10 to the third, right? And 10 to the negative. Okay, so milligrams is 10 to the -3 grams.
Yes.
Micrograms is 10 to the -6.
Okay,
They're
now
the
I see
same,
why
so
it's
you
3.
subtract, that gives you 3, right?
3.
And you're going,
Yeah.
the direction is still up or down. So you're going up. Yes.
Yes, that would be
So then it's -3
-3. Okay.
milligrams. Okay, so there's your answer. So you're just multiplying 30 times 125 times 10 to the -3, or you can just leave that one alone and then do the math afterwards. Okay, so I get 30 times 125 equals 3.75 times 10 to the third, and see the -3 will void that, so the answer is 3.75 milligrams. You got that?
3.75.
Mm-hmm. All right, look at the next one. Prescription pain reliever. Hold on, I'm inserting table. I can't talk and do this at the same time. Okay, contains 30 milligrams of codeine per tablet. Okay, so here's an internal conversion right here. See, they're telling you the package directions recommend taking no more than 8 tablets in 24 hours. You see that? How many grams, there's the question, of codeine is the maximum recommended dose per day, So that's the question. All right.
So we
So
got to convert
we start
mg to g.
with 1 day, right? And then the first thing that we have that matches the day or 24-hour period is what?
8 tablets.
That's right. So 1 day on the bottom, 8 tablets on the top. And we're just going to call them tabs. Okay. And then the other one, see how the other one matches now? 1 tablet, right, on the bottom. And how many milligrams of codeine?
30 milligrams.
And then they want it in what?
They want it in
Grams.
grams.
So then 1 milligram is equal to 10 to the negative 3 grams. Yes?
Yes.
Okay, there you go. And like I said, sometimes if you just multiply, you don't have to worry about the 10 to the negative 3. So just to see 8 times 30, there's nothing to divide it by. So I
Will
get,
it be 2.4 times 10 to the negative 3?
okay, so I get 2.4. Okay, this is what I get. My answer is 2.4 times 10 to the second, right? That's what I get on my calculator without the negative 3. And then remember, times 10 to the negative 3 would give you what?
2.4 times 10 to 1?
To the negative 1, right?
Negative 1?
Mhm.
Ooh.
Which is equal to 0.24.
Hold on. Back.
Back.
Okay.
She says. Okay. So when you like I said, if you don't have a calculator like mine, that you can elevate, do the EE thing, this is how I do it. So 8 times 30, right? So 8 times 30 gives you 240, right?
Yes, that's what I was at.
Okay, so let's do it that way. 240, okay, right? Times 10 to the negative 3. And we want to make it 2.4, right? So 1, 2, we're backing it up 2, so we're adding 2 to this one, right?
Yes. So then
And
it'd be
see, that's still the same thing.
Oh, okay. I see why we
You
did 2
see?
instead of, okay.
Okay. It is the same. It is the
And
same
then-
exact thing.
so
It's
then-
just that I have it set on scientific notation, so I'm kind of cheating a little bit.
So it's okay, 0.24.
Yeah, so it's negative 3 plus 2, right? Because we
negative
moved it, right? We moved it so that it's correct scientific notation, and then they gave you to the negative 1. And that, if you want to convert it to actual grams, it's 0.24, right?
Yes.
All right, so these are easy. I think you guys know this one. What matter represented by each of the following? Ice is solid, right? Clouds in the sky would be gas. Hydrogen in the sun would be plasma. Rocks would be solid. Air would be gas again. And vegetable oil would be a liquid. Yep. Okay, that was easy. All right, now. Well, I mean, anybody knows these. So classify the following as a chemical or physical change. Okay, so electrolysis of water, that means you're breaking water up. That's a chemical change. Formation of fog. All it is condensation, right? So it is a physical change. Rusting of iron, that's chemical, right? Separating alcohol and water, that is also physical because of by boiling point. Burning wood, that is definitely chemical. In converting sand to glass, it is only physical. Okay? Because you're just melting. Melting,
Sorry.
converting sand to glass is fine. You're melting the sand and then re-solidifying it to make glass. So that's it. All right, this drawing thing, you don't have to draw it. Obviously, you can just go to, let me show you where it is. All right, ooh, let me see. Let me go back to this thing. You can still see me, right?
Yes.
Okay, so I'm trying to show you where it is so that you can just go get it. There we go. All right, does it say, which one does it say to do? Energy?
Energy, temperature versus energy.
Okay, so that is the first one. I think it's this one. I want to say that's the right one, but if it says energy on it, then that's correct. Nope, that's time. Oops, wrong one. It's the other one. It's not the phase change chart, it's the other one. Diagram. Nope, that's not it. Where are you? There's another one. Where is it? It's above that one, isn't it? Okay, phase change diagram. Yeah, that must be it. Yeah, this is it. Okay, see how it's temperature and energy?
Yes, I remember this.
Heat is energy. All right, so just Control C, which means copy, right? I hope I copied it. I don't know. I'm going to say it again and see if I can put it into that sheet. Let's see. I'm just going to attempt it. Nope, it didn't. But you can copy it. You just got to download it. I didn't download it, but that's where it would go. Okay. And then label it for yourself, but I think it's already labeled. So basically, you just need to know that one is what this is saying. All right. All right. Now, the next one, it says for each of the following, right, whether it's a mixture, solution, or a compound. Soda pop. That's a solution, right? Baking soda, that's a compound. And I know I'm going weird. Sugar is a compound. Milk, that is a mixture because it is a hetero. Pizza, definitely a mixture, right? Muddy water, that is a mixture, a suspension actually. And bronze, that is a solution. Solution. Why is it solution? Because they are not combined completely, but they are very homogeneous. All right, so this definition, that's up to you. Yeah, I mean, that's easy. You just find them. Solid, liquid, gas. All you have to, and I always add plasma to it. So I'm going to insert one more row below. There we go. We're going to add plasma. I don't know why every time it goes away, and that should be 1 through 4. All right, so just imagine they'll say 1 through 4. All right, so solid, the temperature in a solid is the lowest, right? So notice it says 1 being the lowest, so that's the lowest. Then the liquid would be next. They're kind of in order on purpose. Kinetic energy is same as temperature because it's the movement of the molecules that give you the temperature, right? So again, 1, 2, 3, 4. The distance between the molecules is less in a solid because there's less movement. So 1, 2, 3, 4 again. But the intermolecular forces are highest when it's closest because they're closer. And there you go. That was easy, wasn't it? It's just one that's revert. All right. So, all right, periodic table. Okay. For this one, we do need a periodic table, which I have in my hand. So let's look at it. Remember, radius, atomic radius increases, is the only one that increases this way, which is to the left, right, and down. So if on the periodic table, bismuth is more to the left or to the right or farther down than phosphorus, then it's bismuth, right? So in this case, it's U. Rubidium or antimony, okay? Rubidium, it's all the way to the left, and antimony is closer to the right. So definitely rubidium is going to be the largest. Why? And you can say this. I mean, just describe it in words, right? Because, you know, the radius increases to the left and down the periodic table. That's all. All right, now, magnesium or magnesium ion. Remember, when you get positive, you're losing. So the one that's largest is magnesium. The one that's largest over here is selenium. Now, more electronegative. Now this time, we just need to erase these and go the other way, because electronegativity increases this way and up. And it does not include noble gases because they don't react. So, all right, so let's look. Selenium or gallium. Selenium is more to the left, to the right, sorry, than gallium. So selenium is going to be more electronegative, right? And then chlorine or astatine. Chlorine is farther up, so chlorine. In electron affinity, same thing as this one. So yttrium or technetium. Okay, yttrium is almost to the end of the periodic table. Technetium is kind of in the middle, so technetium. And then helium or radon, definitely helium. This one does include noble gases, okay? So there you go. That's it. Those are your choices. All right, now let's complete the next one. And I could have highlighted them, I guess. I don't know why I didn't. It's because I had that thing on me. But we can still highlight them. It was bismuth. And it was rubidium, right? And then this one was magnesium. And this one was the ion, because the ion increases. And then this one was selenium and chlorine. And this one was technetium and helium, right? All right, there we go. I should have done it that way to begin with, but I didn't. All right, and there you are. Now this next one, ooh, you remember these? All right, for this one, the number of electrons and atomic number is going to be given to you. Obviously, it didn't get given to you at all, the number, because I wanted you to find it. So potassium, the atomic number is 19, right? Which means that the number of protons is 19, because these two are always the same. I'm going to highlight the two that are always the same. You should never change these. The mass was given to you on the thing, so that is 39. Neutrons, you just subtract these two. Mass minus protons gives you 20. And the electrons, you know how many, because the positive 1 indicates that you lost 1, so it's 18, right? Remember that?
Yeah, we do.
All right, so calcium, it is 20, if I'm not mistaken, yep. And then this says 41. So obviously that's 20. Neutrons is going to be 21. And electrons, well, they didn't change them, so 20, right? Notice there's no positive or negative on there. Okay, gallium, where are you, gallium? 31. So the protons is 31. The mass number is given to us, 69. The neutrons, 69 minus 31 is 38, yes? Yeah. And electrons, we lost 3, so it's 27. See? Chlorine, that is 17, right? 17. And so protons is always 17. The mass was given to us as 37. Neutrons is going to be 20. And electrons, you have one more, so it's 18.
Okay, I'm confused as how we're getting neutrons.
Neutrons, all you got to do is subtract the mass, and I'm going to put that in a different color. This mass number, right, minus the protons. So 39 minus 19 equals 20. 41 minus 20 equals 21. 69 minus 31, 38. 37 minus 17, 20. You see that?
Yes, I see now.
Okay. And then the electrons is just a matter of whether it's positive or negative, right? Oxygen.
Right.
So oxygen is what number?
8.
8. So that means we have 8 protons. And since we have 18 mass, we have how many neutrons?
10.
10. And obviously nothing changed as far as electrons go, so it's 8, right? Uranium. Oh, this one's a fun one. Uranium, where are you? 92. Okay, so then this is 92, because remember, this is what gives the identity to the atom. So you know which atom it is if you count the number of protons. So that's why they never changed. The atomic number and the protons is the same. Right, the mass was given to us is 235. And I'm trying to find out the neutrons. What did you get?
143.
143. Yep.
Yeah, I got that too.
All right. And how many electrons?
92 minus 4.
Mm,
Are you add 4?
No, you're subtracting. Positive.
88.
88. 89, 91, 88. That's right.
88. Correct. All right. And there you go. That's how you do it. And now if you were asked whether it was an isotope or an ion, well, remember, isotopes are different from the periodic table, right? So this right here is the same as the periodic table. So no, it's not an isotope. This calcium is 40 normally, so 41 would be an isotope. Gallium normally is 72.3. Oh, so that's germanium. So gallium normally is 70, so 69 would be an isotope. Chlorine normally is 35.45, so it's 35. So that would be an isotope also. So with oxygen and uranium, where are you, uranium? Uranium is normally 238. So uranium-235 is also an isotope. And that's how you know. Just this number right here tells you if this is an isotope or not, because that's your mass. Oops, sorry, not all of you. I just wanted to highlight the one. Okay, I just wanted to highlight the 18. That right there is your mass. And if you compare it against the periodic table and it's different, then you know that's an isotope of oxygen, which normally is 16, right?
Yes.
Okay, so that's that. Now, this one is one of those problems where you take the percentage and take it and convert it to non-percent, remember? So 107 times 0.518, is it? Divided by 100, in other words, right? And then you add it to the next one, which is 109. Oops, I said add it. Sorry, add it. 109 times the percent here is 0.482. And that's it. And they want it expressed to 3 decimal places. So clear is 1, and you can do it just like it is on the written. So if you do it like that, you should not have to, look it up and write it down and then do the next one and write it down and all that.
I got 107.964.
107.964, that's what I got too. And what is it on the periodic table? Da-da-da-da, silver, 107.87. So it's not exact perfect, but guess what? It is given to you by a mass that is not exact either, right? See?
Right.
And that's why you only have this.
What is this called? Percent what?
This is called average mass. This is average molar mass, which is the same thing, but this is average mass. So you know how in your periodic table you have the bottom number that the one that I gave you anyway, the bottom number is the mass, the average atomic mass, and that's what that is. That is the average atomic mass of silver, which is not to be confused with mass number. Mass number, that's why we round it. See, that would be 108 for silver, because we cannot have half a proton of half a neutron, right? So we add them all, right? And that's how we know. All right, the next one. Ooh, long and short electron configurations. Remember those. Okay, so phosphorus, and I'm just going to write it. 1s2, 2s2. And I know I'm not putting it up, but it's just hard to do all that and write at the same time. And phosphorus is on 3s2. Okay, so 2p6, 3s2, and 3p3, right? All right, so this is up. All right, so these are basically a mapping of every single electron that belongs in phosphorus. Phosphorus has how many electrons? Well, what's the atomic number?
15.
15. Okay, so if you add 2 plus 2 plus 6 is 10, plus 5 more is 15, correct?
Yes.
So see, I'm adding all of the superscripts. And that's correct. So that gave me the number, the exact number. So this is a correct Lewis structure. Sorry, not Lewis structure. This is a correct electron configuration. If you just look at the ending, right? That's this. And take this as your core electrons. That core electron can be represented as a noble gas. Which noble gas is it?
Neon.
That's right. So basically you just, oops, I put brackets instead of, keys instead of brackets. There we go. And then you just put 3s2. So basically you just copy this down, right? If you had the whole thing. And there you go. See? So basically, the core electrons don't have anything to do with reactivity, right? So it's okay to represent them like that. Now, the other thing that is good to know is that this right here gives you a lot of information about that atom. And you notice that it has 3 levels, 3 electron levels, as told to us by this 3, which I'm going to make red. Right? See that?
Yes.
And it also has 5 electrons on its outer shell, as told to us by this one. And I want to make it blue. What color do I make it? Purple? Ah, purple looks good. Okay, well, no, actually, purple looks like the same color almost. All right, but there you go. See? So if you add those, that's 5. And that's how many electrons are on the outer shell, which is the 3rd shell. See? It's very easy to look at that. All right, so let's look at this next one. That's chlorine. Chlorine is going to be, ooh, what in the world did I do? Not what I wanted to do. That's for sure. Okay. Kitty cat, what are you doing? You're cute. Yes, you are. Sorry, my kitty. She likes to mess around with me. I mean, come just visit me when I'm busy. Okay, so, let me figure this one out. See, every time I click on that, it messes up. All right, I'll just do it right here. All right, so 1s2. So this one would be 1s2, s2, 2p6, 3s2, and chlorine is right after this one, so it's going to be 3p5. All right, so did I put 3s2 yet? Yeah, I did. Stop messing with my pen. Sorry. Just like a bird is chirping, mine is playing with my stuff. She's a cutie, but man, you can hear her messing around with the blind. You crazy kitty cat. All right, and there we go. So that's the whole thing, right? Again, the yellow part would be neon, right? We know that part. And the green part would be the valence electrons. So we know that this is neon. Where are you? Neon. And purple, of course. And in little. That is so not the right color. All right. Neon and, of course, these. And you notice that they're pretty much the same, but they're also in the same area. And that's what the point of this exercise is. That you see they're both on the 3rd level, just 2 more electrons. And that's correct, because this one had 15, this one has 17. See? Okay, so argon is going to be 1s2, 2s2, 3. Oh, oops, sorry, 2p6, 3s2, 3p6. All right, so this one is argon. Argon is still also on the 3rd level. So these are our core electrons. So see, most people think that you can just write argon because argon is a noble gas, but no, because you're not telling me anything about this atom if you do that. So when you are writing argon, you need to give me the same information you gave me before. So neon again, right? So this same information, pretty much, we just copy it and we paste it down here. Why can't we? Can, because it is the same except for one thing. We have a 6 here. See, that's it. Now fluorine, This one is interesting because we need to actually do the whole thing, the whole flooring, before we can actually get this one. Let's see, that was a 9, I think. All right, so 1S2. We need to do 2S2. Flooring is 2P5. Okay, so that's flooring by itself. But -1 means you added 1, right? So we're going to add it to the one place we can, which is here. And we're going to also change the color when we do that. And we are going to change the color so that we note that this is not its normal number, but instead it is an added electron in there, all right? And if we were to do this as a shortcut, what would it be?
HE.
Helium, right? Which is not much of a shortcut, is it?
No.
But it's still it's shortcut. So we need to, if we were to do it, we need to do it. So now the shortcut becomes HE, right? So again, it's doing in red and in high. That's weird. Okay, that's because I changed all of it. And let's make it black again. Okay, and then just copy this.
2S2, 2P.
Mm-hmm. Yep. And there it is. Oops.
6.
Okay, let's make this one back a little bit so that way we fit. Otherwise, we don't fit at all, do we? All right, there we go. All right, so sulfur -2, which is right here, which is in a very strange place. Let me just get these out of here. There you go. That's the problem, is this guy is in the wrong place, so I can't keep going. There we go. And so is this one. They're all in the wrong place. Oh boy. What a mess I made. It's because I'm trying to type and it doesn't like me typing too much. I'm just putting it back where it belongs. There we go. All right, now sulfur -2, we're going to have the same problem, right? You're going to have the 1s2, 2, oops, 2. Yeah, I'll fix it later. 2s2, 6, 3s,
3P5.
and 3p4, right? And that's all of that.
Right.
I'm going to change it to the right color because that's weird.
1,
It
2.
needs to be black and it doesn't need to be that small. Okay, there it is. That's for that one, right?
Hold on. If we subtract 2, we add 2, right? So we
Yes,
3P4.
you are adding 2, right? Exactly. When you have -2, it doesn't mean you're subtracting. It means you have more negatives than you have positives, which means
Right.
you have more electrons. Right? That's why a lot of people get confused with the negative and the positive. Okay, so this is sulfur itself, right? But if we add 2 electrons, they fit right here. So we're going to put a 6 there and we're going to make it red. That way we know that we have added to that one area. And that is correct. We did. All right. And then the last one's helium, which is super easy. It's just 1s2. And there is no shortcut for him. Why? Because he's already the shortcut. He's the shortest cut there is. So there is no other. All right. So that's how you do that. Now, it also says write orbital configurations. So which 2 orbital configurations do you want me to write? It's just 2 of them. No,
Bless you.
thank you.
Let's do D. And E.
Okay.
The hard ones.
B and D
D and E.
and E. Okay. All right, so let's do those. Basically, these I'm gonna have to do with my handwriting, as you know. Okay, so B is this one. Oops. Nope. This is so annoying when I'm trying to do something pretty and it doesn't work. Maybe I need to make straight lines. That's what I'm gonna do. All right, there we go. So we're gonna do one line. Oh yeah, see, that's so much better. Two. Nope, it doesn't want to keep. Oh, okay, nope. It doesn't like to do that either. Okay, so let's skip that one. Clear my drawings because they're ugly. All right, so I'm just gonna do weird lines, sorry. It's the way it's gonna have to be because I can't. All right, so that's 2S, this is the 2P. This is the 3S, and this is the 3P. That's for chlorine, right? Okay, so chlorine, this is the 1S. It has 2 electrons in it. So this is 1S, and that's how you would have to do it. Then the 2S, and that would be another 2 electrons within that one. And all of these are the 2Ps, so let's just say 2P here for all 3 of these. Remember, each orbital can hold 2 electrons, right? So these are pretty full, but the law says that you first fill them halfway and then you come back and fill them completely if you have enough of them. And in this case, we have all 6, so we do. And this is our 3S, right? And this one is 3S1 and 2. And the last one, which is 3P5, right? That's this one. And we're going 1, 2, 3, 4. Oh, sorry, that's the negative one. And 5. And there's your 3Ps. And that is the electron configuration for this guy. These are all 3Ps. Sorry, just there you go. That's that one. That is chlorine. Okay. You notice how chlorine ends as a negative spin. That's the last electron that's in it. Now, when you do fluorine, well, you wanted sulfur. Okay, so let's pretend that this is sulfur right here. All I'm going to do, so I don't have to rewrite it, is take 1 electron out, right? Because it's 4, yes? 3p4. And we are going to add other electrons, but in this case, our electrons are borrowed from somewhere else. So we're going to make them a different color. Let's make them blue. And see, that's why the -2. Those 2 are extra. And they're negatives because they're electrons. So there's your 6. You see that? Got it? You want me to do another one? Or is that
You all
good?
get it?
That is sulfur -2. That one. This is why it's negative. It's because you got those extra 2s. I guess they did. Nobody's saying anything. Do you
Okay.
want to do another one, or is that good enough? Or
I think that's good.
okay.
I think.
All right. Okay, so now it says name at least one trend among each of the following periodic families. All right, so what does that mean? Trends. Trends just means, remember those arrows that I always draw?
Yes.
That's exactly what it means. All right, so the alkali metals, which the alkali metals are group 1A, right? So 1A. And what we need to say for this one, I would do it on, and let's just type it in. All right, so 1A, this is group 1A. Just putting that in parentheses so you remember that. All right, so for this one, you could say that, let's see,
Shiny and brittle.
I guess, no, trend. Trend is atomic radius increases, going down, right? The family or the period, right?
I was talking about properties.
Yeah.
Sorry.
That's what trends are. Yeah. All right. This is 2A, right? We know that. All right. So in this case, let's say ionization energy, just to give something. Oh, wait, no, because the halogens is going to be ionization, and they're the only ones that have that. All right. Let's do not electronegativity. I like that for the halogens. What do we do this? Ionization, no, ionization energy, I already said no, the other one. Okay, let's skip that one for a minute because my brain's not working right now. 7A. Okay, so halogens is 7A. This one is going to be electronegativity because they're the most electronegative area, right? So electronegativity increases, decreases, or whatever. Electronegativity. There we go. Increases or decreases, up to you. We're just going to say decreases going down the period, right? No, not the period, the group. Or the, I said period here. I meant group. I said period. That meant group. That is a group, not a period. Periods are horizontal. We're talking about vertical. Noble gases, that's 8A, right? Okay, so 8A, we can say that electron affinity, that's the one I was trying to think of on that one, and I couldn't think of that one. All right, so electron affinity, that's, no. That's for 2A. I started typing in the wrong one. Okay, so this increases, decreases, up to you. I'm just gonna keep going down the period, so it's gonna be decreases going down the period, the group, yeah, period, okay? And the last one is ionization energy. Increases or decreases, sorry, going down the group again. So there you go. That's how they all are. So you can, like I said, you can write increases, decreases, up to you, as long as the direction's correct, right? And that's what you want to do. So if it increases, it's going up. If it decreases, it's going down, except for the alkali metals, which is going down the group is correct. In this case, you notice this is the only one that actually increases. That's the difference. These are meant to be this way. This is an increase. The other ones are all decrease, going down, see? And that's why I made them all go down, is so that you could see that they're exactly the opposite, right? Come on, I don't want to underline you too. One highlighting is good enough. All right, so there you go. All right, so now the question, this one pretty much relates to what we were just writing. It says, if a noble gas could form a +1 ion, which one would it form most easily? Okay, so notice that is ionization energy, right? You notice it says it decreases going down the group. So which one of the noble gases would form it an ion more easily would be radon. Why? Because it's the one with the lowest ionization energy. So you need to just write that down. The answer is radon because it has the lowest ionization energy of the noble gases. There, how's that? With respect to electrons, how does an ionic bond differ from a covalent bond? You remember this? Ionic bonds are formed by a transfer of electrons from the metal to the non-metal. And covalent bonds form by the sharing of electrons between two nonmetals. There you go. How's that?
Okay.
All right. Ionic, nonpolar covalent, or polar covalent. Okay. You notice that description above kind of told you which one's which. So we're going to highlight ionic in yellow, non-polar covalent in green, and polar covalent we're going to do blue. Okay.
Okay.
All right. So the very first thing we know is the ionic. That one's easy. Metal and non-metal. Metal and non-metal, that would be this guy. And no, it's not blue. It's meant to be yellow. Sorry. There we go. Yellow. There we go. All right. That one's a metal and a non-metal. So is aluminum and oxygen, right? Those two out of the picture. That was easy because metal, non-metal combination, it's always ionic. All right. Now, for the other ones, they're a little more difficult.
H2O is always polar, correct?
Yes, we know that, but we know that because we know that.
Right.
But we actually need to look at the Lewis structures and see if we have any lone pairs around the central atom of each one. So to do that, we would have to do the math, right? So that was 12, let's see, it is 6 electrons from oxygen plus 2, oops, that's a plus 2 hydrogens gives me a total of 8, yes?
Yes.
When we make our bonds, which I'm going to do just a really quickie right here, oxygen in the middle, hydrogen, oops, hydrogen, man, my nails are too long, and so it doesn't hit the screen right on, and it makes this little weirdness. Hold on, let me clear all that. Let me see if I can do it with, this is why I've been using the mouse, which takes a little longer, but at least it won't do that anymore. Okay, so we do the hydrogens, right, on each side of the water. All right, and I know you know that this is polar, but we're about to find out why. All right, so now, since we used 4, right, we subtract 2, because 2 bonds, right, times 2, which is 4. So it gives us 4 left. And remember, hydrogen does not like extra electrons because it already has the number it needs. So the only one that needs them is oxygen. And there you go. We do have lone pairs around the central atom, hence it is polar. That's right. Now let's do NO2. I'm just gonna keep going on the same line, you know, just remember which math is for which. All right, so nitrogen is 5, right? Plus, we have 2 times 6. That's 12, I know, but then gives us, okay, that is not good. Okay, 2 times 6 is 12. And plus 5 is 17, sorry. All right, so see, this is why I said that's not good.
Yeah.
Because you notice that this is an odd number.
Yes.
Odd numbers are no good.
No.
Because, yep, they're confusing. But we're going to do it. Okay, so nitrogen is in the middle. In this one, right? So nitrogen, oops, okay, so make it big, I don't care. Okay, nitrogen, oxygen, we have 2 of them. Okay, now we used 4, so we'll just subtract 4 from that. And like I said, 2 times 2, 2 because it's 2 electrons per bond, right? So that's why I do that 2 times 2, which is 4. That gives us 13. Right? All right,
Yikes.
13 electrons left. We are going to now put the double bond, the double bonds, no, the what you call them, the lone pairs around all of these. And you notice that we only have 1 left. And that goes for nitrogen. So this is not quite correct, is it? Because nitrogen's going, hey, where's mine? I need more. Even if it's only 5, it's still not enough. It could be 7. So we remove this one and make a double bond. There we go.
He still needs another one, doesn't he?
He would.
Another.
He would. And this is why I said this is problematic because it's an odd number. So when you look at this, you can see that this is going to be polar, right?
Right.
Because of that 1 lone pair. But it's just unusual. It should be NO2 negative, I think. I think it's what it's supposed to be. Let's just say it's NO2 negative because that is nitrite. So then that would make it 14, right? And then we would have that. I think it's a typo myself. All right, so there you go. So we know this is polar, right?
Yes.
Because it has lone pairs. So we are going to make him a polar guy. Just remember to put that negative up there. Otherwise, it makes no sense. All right, so we know he's polar. CS2, carbon and sulfur, okay? Let's clear that guy. Don't forget the negative is up here. You know what? Let me write it in there because it's bothering me. Yeah, that's got to be a negative there. Oh, I'm trying to put it, come on, negative. And we're just going to put it up, above. Oh, what? That's crazy. Oh, I see what's going on. That's a negative. So it's doing this. Yeah. Man. That's what it is. It's the size. All right, now we can bring it up. There we go. No, it's still in a weird, isn't it a weird place? Why is it doing that? It's not letting me bring it up. Anyway, just imagine that's probably what happened. It didn't let me do it, so I just ignored it. Okay, so carbon. How many?
4.
Plus, how many do we have of sulfur? Oops, plus. We have
4.
2. 2 times 6 for sulfur,
2
right?
times 6.
Yeah, because there's 2 sulfur
Oh, I see. Yes.
and they're in 6. Okay, so that gives me a total of 16, correct?
Yes.
Okay. So let's write our little Lewis structure. Carbon, sulfur, and sulfur. Right? We just used 4 of those. So we subtract those from it. So minus, and like I said, 2 times 2, only because of the bonds, right? That gives me a total of 4, no, yeah, 12. I don't know how to add 12, right? All right, so now we are going to say sulfur gets all of those little dots. That's not right. Why is it not right? Carbon's going to be going, hey, baby, you forgot me, isn't it?
Yes.
So let's put them on there. But you can see carbon's not happy. So we're going to erase one of those and put a double bond. Is carbon happy yet?
No.
All right, then I guess we need to erase the other side too and put another double bond. And see what that becomes is a linear.
Linear.
That is
Yes.
non-polar. You see that? Mm-hmm. So now we need a green one. Where's green? Okay. All right, let's come on, green. Come on, green. And that would be non-polar covalent. And the last one we have is BF3. And remember, boron is an exception to that rule of the numbers that we need. Boron is in group 3, so it really only needs 6. So let's do the math for boron. Boron is 3, right? It brings in 3. Plus we have 3 fluorines times 7 each, right? So that's 21 plus 3 equals 24. Okay, so we have 3 bonds. I might as well just put that minus 3 times 2, right? It's equal because it's going to have 3 bonds. And that's going to give us 18, yes?
Yes.
Okay, so that's all the math we need. All right, so let's go do the boron. All right, so boron's in the middle. And we have fluorine, and I'm just going to do the other fluorine to the bottom. All right, so fluorines are right here. All right. And we have exactly 18, which is what we need. 1, 2, 3, 4. And boron's not going to be complaining because boron is an exception and it only needs 6. How many does it have? 6.
4.
No.
What? Oh, 6. I see now. I see now.
6 because you got 2, 4, 6, right? So we're good. So that's another nonpolar covalent. You see that? Because it has no lone pairs about the central atom. So there's our little, there's our little nonpolar is green. So that's you. And there you go. That's how you know. All right. So we're going to probably stop here for now. And we will come back to this one next time. So I'm going to save it right now. File, save as. I'm going to save it on my desktop. This is why I end up with so much junk on my desktop. I do. Hold on. Let's go back again. Yes, got it. No. Okay. Save. No. No. What? Did it just go away? No. Please tell me it didn't go away. No.
I'll remember.
Yeah, I know, but I was going to try to leave the It went away. Okay. I said yes, save him, but it didn't save him, so that's okay. Anyway, so now let's go because somebody wanted to know how to do the Lewis structures. Can you tell me which one it is that we're looking at? Was it you, Kashonda, that you wanted to look at?
Yeah, let me see what chapter it is.
Yeah, I need to know. I don't know by heart. Oh, you're so cute.
Did you say 5?
I think she
I
said
think it
5.
is 5.
Yeah, I think she said 5, but I just want to make sure
Yeah.
that when I get
I think
there,
there's
it's the
also,
right one.
I think there's also some on chapter 8. 'cause that
Okay.
is
8
kinda under-
too. Yeah, it
Yeah.
is
Okay.
8. Yeah, 5 and
Once
8.
I show you how to do that, you're gonna say, "Oh, that's so easy." But you got to do them a certain way, or it doesn't work. And that's the picky thing. Where are you? I must have passed connect long
Well,
time
I
ago.
even tried to do a little guided. I even did work.
Yours worked? I'm sorry. Valerie, what did you say?
I think she said it didn't work.
Didn't work. Okay, now I'm gonna show
Yeah, I
you.
think she said it didn't work. Yeah.
Okay, I'm gonna show you.
Yeah, I tried. It gives you instructions. Like it lets you click up for the instructions. And I
Yeah.
followed the instructions and everything, and mine matched because I even Googled to make sure I had the answer right, and it still said my answer wasn't correct.
Is it chapter 5 assignment or application problem?
8. It's
8?
chapter 8 assignment.
8. Okay. She said it was 5. Okay. 8. Gotcha. Ah, no. It did what it wanted. I was just going up. Okay, excuse me. Here we go again. Chapter 8. 8 assignment or application problems? Okay, 8 assignment. All right, let's go and do this as a student. And I'm just going to look for that one. Hopefully we'll find it pretty quickly. Okay, continue. Oh, okay. NH3. All right, so we would do the math, right? And we would end up with NH3. Draw the structure, okay? So we want to put an N in the middle. So that's what the A is for. You put in blank and you put an N, right? And then you make bonds, 3 bonds. So we're going to do 1, 2, and 3. Okay. And then we need the A's to touch. So that would be, see how it touches, it becomes blue. So that's your H's. See? That's how you have to do it. You have to touch it. And then put your lone pair where it needs to be, right there. Oops, come on, lone pair. What are you doing? Undo. Hold on. It's hard to see it this small. Let me make it bigger. There we go. Oh, it still didn't make it bigger. Okay, let's control plus it then. There we go. Now, we need a lone pair. So we just click it on there and put it. There you go. There it is. Oops. Ah, undo. That's NH3. You see it? All right, so let's save it. Okay, it says.
Yeah, I see that you was able to make like the little lines. You was able to control it. Was you holding it and pulling it, or because when I put it on there?
Yeah, I just used these lines. We'll do more. Hold on. Okay.
Yeah, because it like on mine, it was going on the paper. Like when I click on it, it's going exactly like that shape sideways or something.
Save. Okay, so do I say save and exit? I can't see.
Yeah.
I can't see my instructions. Save and exit. Okay.
Yeah.
Thank you. And it should have put it right there, but it didn't. See, I think it was. Oh, that's just part 1 of 5. Okay, next part. Okay, return to question. I did make the stupid structure. Edit structure. See, it went away.
No, it's still on there.
Okay, but it's correct. I know it's saved. There it is. See, it's on there. Okay, so I just closed this. I couldn't see, so that's why save and exit was wrong. All right, so see, there it is. All right, so check my work. Boom. It says incorrect. Take sum of all valence electrons, distributed. Octet rule, yep, I know, and I did that already, and it's got the lone pair on it. Okay, let me see, edit structure. What's wrong with you? The lone pair.
Was one of them supposed to have a double line?
No, not in this one.
Okay.
Let me make sure. Let's see, edit. I don't want to reset it. Oh, I don't want to reset it because then I have to redo it. Okay, what is wrong with you? Okay, so I want to undo that. How do I undo you? There we go. Nope. Okay, what? See, there's the lone pair. This lone pair is weird. I can't erase it, so I gotta have to reset it. All right, let's just say, okay, fine. Let's do it again. All right, so nitrogen. What on earth? I don't want a lone pair. Sorry, I have to be on the right thing when you click it. That's the main thing. All right, so nitrogen. And I put the bonds, right? I just did them straight, see? Just take it and pull it, make it straight as much as possible. And then those are your bonds. They're fine, I think. Maybe that might want that one to go up a little bit more. Nah. Nope, undo. I don't want a double. All right, so let's go and do the hydrogens now, which is at the end when they touch. You put hydrogen on there. I did this many times before and it worked very well. And then we just want the lone pair. Okay, so if I click on this guy, I need the lone pair to be on the top of it. Okay, no, I don't need you there. Okay, so I need lone pair. That's what it is. And just stick it on their top. There. Now save it. That should be correct. All right, that looks good. It's not perfect, you know, but it doesn't have to be perfect. See? It's correct, right? All right, H2CO. Okay, so this one's going to be the C in the middle, because C is always in the middle because it's lower electronegative, and hydrogen can be in the middle, but oxygen could be, but carbon is lower. All right, so then we got bonds to the hydrogens. Oops, undo. Bonds to the hydrogens.
Hello.
And then we have a double bond to the oxygen. And then we got hydrogen, hydrogen, and oxygen. And carbon is happy, but oxygen isn't, so we need 2 lone pairs there. So let's go back to you. And there we go. That should be it. And let's see if it liked it. It says it's not. Take the sum of all the valence electrons. I know that's correct, but let me see what's going on here. Yeah, I did. I did. Everything is right. So why is it telling me it's not? That's so annoying. Okay. 2 attempts left. Okay, next part. I'm just gonna say it's correct. Yes, move on. Okay, see, it put it straight. Whereas this other one, it put it crooked. So annoying. All right, this one, you got a carbon. Okay, this one's pain. This one's a pain in the butt. All right, so carbon's in the middle always. And then this carbon is bonded to 4 things. So we got bonds to do, bond going up, bond going to the side. See, I'm dragging them down. Bond going to this side. All right. And then the CO. Okay, so that's a double. All right, so we got CH3, 2. Okay, that's too many bonds. Undo this bond. I'm going to, oops, undo that bond. There, that one's good. And just double bond this one. Okay, that's your oxygen. All right, so each one of these is going to have a carbon. Oops. No, you stupid thing. Undo. I keep forgetting to push the A. All right. Nope. That's too far. Oh, Lord. That's like in the wrong place. Undo that, aren't you? Okay. See, you got to touch it and it makes that color and then it's okay. And then enter. And then this one, touch it. Carbon. Enter. And then this one, oxygen, enter. And this one, now this one needs hydrogens on it. Oops, nope. Sorry, this guy. All right, so we need a hydrogen straight, and a hydrogen on that one. And then same here. It's gonna make a mess because it's not gonna like it the way it is. Yeah, see, it's crossing. It's not gonna like that. Okay, but the bonds are, for some reason, the bonds are just as long as they're gonna be, period, you know? Can't make them any shorter. Nope, undo, you stupid thing. I clicked A. All right, H here. H here. Carbon always makes chains. See, this is not going to be good. I know they're not going to like this one because it's crossing the H's. So it's going to want you to rearrange it. So I think I can move this guy over. Can I? Undo you. Okay, where is a shift? There's an eraser. I didn't notice that until just now. Okay. Trying to figure out how to move him out of here because he's getting in my way. This hydrogen doesn't have a hydrogen yet. This one has too many. Okay. This one is the one that doesn't have a hydrogen, but it won't let me put a hydrogen on it. See how it's crossing? It's not gonna like that at all. And this carbon and this thing are not touching. That's weird. Huh. Interesting. Let me erase that. So you can erase them and just move it. I'm going to move it to the other side so it doesn't get encumbered by that one, right? And then there's another C there. Yep, there we go. C there, and H3 again. Okay, so we need the bonds. 1, 2, 3. What is that? Yeah, the isolated bond is not meant to be there. You're right. Let's erase it. See, when it doesn't like it, you erase it. There we go. Because it wasn't a good bond. It's meant to come up from here. See? So if it's blue, it's good. If it's not, don't do it. Like, I'm not sure that that hydrogen, that other one above that hydrogen is good because it's not touching it. You see this one? That's an isolated bond. We want to get rid of this one completely and redo it. When we touch the hydrogen, it's blue. I mean, the carbon is blue, and then bring it up from there. You see that? And that gives you the bond. And then you can put an H. Oops, no, what the heck? That doesn't look right. Gee, that H is in the weirdest possible place ever. Why did it do it there? That's so weird. All right, here we go. At the end, there we go. Now, all right. And last touch is the lone pairs on this guy. So we need 2. 1, 2. And that's it. Save. That should be correct. All right, let's see what it says. Check my work. It says it's not right. Well, it is correct. You know, you notice that everybody's happy, right? It's saying it's not right. And I do not know why it's doing that. I want to see what their answers are. Okay, so they're part 3 of 5. Yes, move on. Okay, so next one is water. Now, water is just, you know, that one's easy. All right, so let's start with O in the middle. And then hydrogens on each side. Touch it and bring it out. Touch it, bring it out. Straight out. There. That's pretty good. All right. Hydrogen here. Hydrogen here. And then do the lone pairs for this guy. Oops, undo. Do the lone pairs for this guy in the middle. There you go. Save. And let's see what that says. That's tiny. But that's okay. Save. Why did it do that weird thing? Why did it make it so tiny? Look at that. But it's fine. I'm guessing it's fine. All right, let's go to the next one. Check my work. It says it's incorrect. Everything's incorrect that I'm doing according to it. But everybody's touching. I'm looking at all of them.
Look at the solution and see what they want you to do.
I'm going to look at the next one. Yes, go move on. I am CH3NO2. Okay. So CH3NO2 and O2 CH3. That means that this nitrogen has triple bonds, 2 oxygens and 1 CH3. All right, so you want to look at the solution? Let's look at the solutions just to see, because that's weird. Where are you, solutions? Where are they? Oh, thank you. All right, so show me. Yes, show me. And watch them be the same like I drew them. Okay, this one, I did that. See? Look at that. Isn't that what I drew? Yes. Isn't that what I drew?
Yeah, it is. That's why I don't know.
The exact same thing. Look at that. The exact same thing I drew. You see that?
Yeah.
Water is the same exact thing I drew. Oh, except they moved it over. But you know what? They shouldn't bothered with this thing because they didn't bother with it over here. Over here, it should be a trigonal pyramid. And this one should be a trigonal planar. So it actually should be, never mind. I'm not even going to go there. It's bugging me. All right, they need to do this better. This is a terrible representation. See, like I said, it's a nitrogen bonded to the two oxygens, and yep, CH3. And one of them has a double bond. Yep.
I'm so glad you're having the same trouble we had, because that was very frustrating.
Yeah, and the funny thing is, if you compare it to mine, they're exactly the same. I mean, exactly. This one is the exact same thing I drew. Exactly. Except for the Lewis dots, one came up on top. You know, doesn't matter where you put them. See, this one too. See, I drew exactly the same thing. That is frustrating. I see where you are with that one. What else? Are there more of these?
Yeah, it's a couple more.
Okay, so let's go to the next
like 3 or 4.
Let's go to the next one and see what we got. Chemical formula, that's not it though, huh? No, that's the formula. Polarity. Obviously, you know which one's polar, this one, because this one's symmetrical. Next, okay. Molecular structure, is this, nope. No, this one doesn't need, this would be wrong because you don't ever get lone pairs on hydrogen. Okay. Predict bond angle, that's easy. Determine number of single bonds, Octet rule obeyed, no, yes, whatever. Increasing order of polarity. That, remember I told you that this is just a subtraction from the ebook. See, the ebook has that table that you want, the electronegativity table. Let's see, just go there, look for it. That's what you need to do with this one. The one I gave you is apparently is not as good as this one. The one that they have here is the one that they want you to use, and it's right there. See it? See how there's the numbers? Right there. So you just subtract whatever you're bonding. So let's say oxygen and fluorine. So the electronegativity 4 and 3.4 would be 0.6. And the higher it is, the more the electronegativity, right? And that's it. So that's how you know which order to put them in. Make sense? Yeah.
Yeah, I guess.
Okay, so look. All right, so you got OCl. All right. OCl. Okay, so let me write these down. I'm going to write them down in a table. OCl. Okay, so you got O. You got Cl. You got F, which I know it's 4. That's it, right? Oh, and H. Is that the only ones we have? O, C, H, L, and F? In all of these? Yes? Okay, so let me go get the numbers. Okay. Where are you, book? This one. Okay. O is, I'm just going to write them right here, right next to it. Get another text box. Okay. O is 3.4, right? Cl is 3.2. Fluorine is 4. And hydrogen is 2.2. Okay. So now we got the table. Go back to the assignment. And now we can subtract. All right, so O minus Cl is 0.2, right? So we just, another table. Sorry, I'm trying to make tables. Okay, so O minus CL is going to be equal 0.2, right? The next one that we have is CCl. Oh, we didn't get carbon. Darn it. There was one missing. Okay, let me go get carbon. Carbon is 2.6. Just remember that one. So carbon is 2.6 minus Cl, which is 3.2, is 0, right? Oh, man. I hate when I do that. Okay, so we start a new one. Cl is going to be, equal to 0.6, right? The next one is F and Cl. That is 0.8. Oh, sorry, I forgot to write down what it is. F minus Cl. That is equal to 0.8. And the last one is hydrogen and Cl. So hydrogen and Cl is equal to 2.2. That's 1, right? 1.0. So the most electronegative, obviously, is that one, right? See, they're in order. You see that? HCl is the most electronegative. So it's this one. This one. HCl is the first one. It says in order of increasing polarity. So the lowest is O2Cl. So this one, that's the right answer right there. See? Do you see why? All you had to do was subtract 3.4. Somebody got thrown out. Oh, Kashanda. Okay, so 3.4 minus 3.2 is 0.2. And then you've got carbon and Cl is 3.2. And it was 2.6. Carbon was 2.6. I did not write that one in here, but I could. All right, so let's just put it right here. Carbon. And it is 2.6, right? All right, so there you go. There's your whole table. So carbon minus chlorine is 0.6. It doesn't matter if it's the right order. It's just a difference. Fluorine minus chlorine. So fluorine's 4, chlorine's 3.2, that's 0.8. And then hydrogen minus chlorine again, it is 3.2. So there you go. That's how you know which one's more electronegative. You just subtract the differences. It's called electronegativity difference, or delta En. And the higher it is, the more electronegative the bond. The more polar the bond, sorry. Okay? All right, let's go next one. All right, let's keep going to that one. All right, molecular structure. Is this another one? Nope. All right, obviously beryllium chloride is going to be this one because beryllium's a beryllium is an exception, right? So it's got to be that one. Bonding electron sulfur dioxide. We just look at that one later. Identify the compound. That's easy. Lewis symbols. That's what you want to look at, is Lewis structures. Okay, that's just that we just did. So you know how to do that one, right?
Yeah, I can figure that one out now.
Okay. Here we go. There's another one. Let's see if we do this one right. N2H2. All right.
Okay.
All right. So 2 nitrogens. When you are doing doubles, and I think I had a thing about that one. Where in the world did it go? Oh, it says it's open, but where did it go? Okay. check. No, hold on. I opened it. Sorry. Okay, I'll just go back. What number was it? Did anybody notice?
10, 13, something like
10?
that.
It was 10.
Possibly.
Around there? Okay, I'll go around 10. It's down here, so I can just go there. 10. All right, single bonds. Nope, that wasn't it. Okay, but it was before that, I think. So it must have been. Polar bonds. Lewis structures. Okay. Nope. All right. So no, it wasn't those. All right. So it must have been more than that. Yeah. Yeah, that was it. It was after. I can see it. It was after that one. Polar. See, now it's going to be different. Yeah. Right, that was that. Didn't even give me one. Did you see that? Didn't give me another one like it. That's because I went out and came back in. So every time you do that,
right, it changes.
It's going to give you a different. Mm-hmm. And it's not giving me anything. Where are you, you stupid thing? It's probably one of the first ones in this one. Because they will always give you one. They can't just not give you any to begin with. I don't see anything with Lewis. Okay, come on. Maybe not. Maybe I'm wrong. Yep, not a single one. That's crazy. All right, let me exit again, get a new one. Yep. Just get a new version. Hopefully we'll get another one with Lewis structures this time. I guess we'll
Oops, I didn't write my attendance in. I'm sorry.
That's fine. Okay, so that is not it. Nope. I can do that later. Molecular structure, nope. Chemical formula, nope. Come on, baby. Ooh, 12:30. Yeah, see, we're going on to the next class already. Hard
Oh,
boiling.
goodness. Okay.
Yeah, that's fine. Melting point of compounds. So far, I haven't seen another one. Oh, man.
Well, thank you for going into the extra time for us, because I knew a lot of those assignments, those small things like that where you have to do the diagrams, it just doesn't, it's not user friendly at all.
It is not. You're right. That's one of the reasons I don't like it.
Can we take this now?
Cengage was worse. Cengage was more horrible than this one. The last time I got, see, the thing is, I don't know who's getting them and who's not, because you notice I've gone through it twice, 3 times now, and each time it's giving me a different version. So whichever version you're getting, you may not be getting one of those. You see what I'm saying? So I don't know who's getting what. Huh, this is weird. All right, so if I just look at the preview, see, a preview locks me in and it gives me the answers. See, because it's my own look as a professor, right? So, well, this is not giving me the answer. Yeah, it is. It's right down there. See it? chemical formula. See, so far, nothing is showing me. Ah, there's one. And this is the one that I did. See, the NH3. This is it right here. Okay. So it is letting me do it. Okay. I know how to do NH3. I mean, I've done it millions of times. And NH3 is not what they did. It is not the way they drew it. It is totally wrong. It is actually a trigonal pyramid. Okay, so we got dots. All right, so let me see if this one will let me actually do it. It wants me to do it at an angle, so I'm gonna do it at an angle. That's one of the things I noticed, that it wanted me to do it this way. See, it should be able, it should let you adjust. No, that's disconnected. It didn't touch. Undo. Let's just undo it. Come on. See, it didn't touch it. It has to be blue. That's the one thing I know. And then this guy, I need these first. Nope, see, that's in the wrong place. Undo that one. Okay, it wants to put him there. I would put them on top, but you know, if you rotate it, they are on top, right? All right, let's see save and see if it'll like it. Come on, save. Save. There, it did save. All right, now let's see, check it. See, it liked it now. You see that?
Oh my goodness.
Uh-huh. It's because it needed to be a little bit crooked. See how I said I would have put it on?
We definitely ain't gonna get them right. I'm just gonna charge it to the gangs.
Okay, so
Yeah,
let me
that's how I
know.
feel.
Let me know to send me a picture. That's what you need to do. Send me a picture of, because you may get two or you may get one, and I'll just give you those because they're annoying. So just send me a picture.
Right.
Send me a picture.
I think I had like three of them. It might have been more than that because I left them all blank. I got it all wrong.
Okay, well, send me a picture of the questions that you got that were.
Yeah, I definitely had 3 or more in mine.
Okay. All right. So when you go back, you can go look at it again, can't you? Once you
I
turn.
don't think I can because mine's closed out unless you reopen it. Because they wouldn't let me. It said I'm out of attempts.
Gotcha. Okay. All right. Because this one, I drew it exactly like they wanted, and it still didn't take it, which was weird. Because I know this one. I mean, it's carbon in the middle. Then you got, oops, undo that one. Then you've got your bonds to carbon. Carbon, you've got 2 hydrogens and 1 oxygen. So 2 hydrogens. They want the oxygen up. Maybe. I don't know. I think they did. So that's a double bond. There we go. And now we've got, oops, I keep dropping bonds in different places. I keep forgetting that I'm doing this. Okay, touch it, boom, put the O there. Touch it, boom, put the H there. Oops, that'd be a capital H. Ooh, that's enough. Ooh, that might have been what I did. Might have not been capital. You know? That's something that it doesn't like either, just like I don't. That's I'm picky about for sure. It needs to be capital or else it's not the correct answer. All right, and then we got two lone pairs, and the lone pair should be, see how it's putting that? It's not putting it in the right spot. It's supposed to be one on this side and one on that side, but it's not letting you do that. What about if I just erase the top one? Oh, nope. There. How's that? I cheated. Save and exit. Let's see. Check my work. Did you like it? No. See? And that's the funny part. It says it's incorrect, but it's not. It's correct. It is very unfriendly. You're right. Okay, guided solution. Let's try guided solution. See what it does. Yes, show me. All right, so look. Let's see what it does. Draw the Lewis structures. We select, we subtract or add, sorry, one, wait. However, for a 9, no, we subtract. That was, no, we add for each negative, and we add. Okay, there we go. All right, that's correct. I didn't see that one. Did you see this one? Okay, so check the work. That was correct. All right, so 5 plus 3 times 2, right? Because there were, no, 3 times 1, because it's equals 8, right? That's how many? Skeleton. Position select. Nitrogen in the center. Bond atoms connected. Okay. Check the work so far. See? It's saying it's good. Now it says draw the structure. See, it's telling you to draw it. You see it? Isn't that what I did? That's exactly how I drew it. Except it says replace the dots for lines. And I did that already. Okay. So we do not want you. We want the next one. I wanted the, why didn't it give me the guided solution to the next one? See how it did, see how it adjusted it up? Next step. Okay, this is the one I wanted to see. Next step. All right, see? All right, so I put it to the side. Isn't that the same thing I did though? What's the difference? That's so crazy. It doesn't matter which one of the bonds you make double. My gosh, that is so stupid. 4, 12, that's 18, right? Oh, plus 6. Oops, 24. Sorry, I didn't see that. Plus 6. Okay. There are 1. No, there's no groups of CH3. What? That is so crazy. No. This is so wrong. All right, no, yeah. This solution, this guided step is worse than the other thing. Because it's telling you the wrong thing. See, it says there are CH3s. There are no CH3s, not one. There's H's bonded to the H. So there are, according to this, is going to be 2 CH3 bonds, two C2H bonds, and 1 C2O bond. It's what it should say. That's crazy. So each bond, that's 6 to 18 electrons remain. Balance satisfies reaction, but the central carbon needs 2 more electrons. Well, paired to form a double bond. Check my work. It says try again. Why? It is correct.
It be giving us a hard time.
Yeah, it is a hard time.
Take it away. We don't need that in our life.
It is a hard time, period. Like I said, just send me whatever the question.
Oh, this the one I already done.
Oh yeah, so send me.
Well, I'm good on this.
Oh, so you don't know how many, do you? I have to check myself, see how many you actually got. That's pain in the butt. Because what I was going to do is I was going to return the points depending on how many you got, you know?
Mm-hmm. I think the second one I did horrible, but the first one did pretty good.
Okay. Yeah, it's because